Chapter 15 is back with a shorter video here just to wrap up the chapter. A couple of quick discussions at the end. Starting with dicarboxylic acids, I alluded to in the previous video what happens if we have two carboxylic acids in the same molecule. And notice on this slide 92 here, those two different pKa values. Even though these are symmetrical molecules and those groups are identical, right, the pKa's have pretty significantly different values. And that's because those protons actually depart one at a time. So they're departing from different species, right? One would be departing from the neutral molecule. And then the second proton that leaves here for pKa2 would be departing from a molecule that's already negatively charged. And this is something that we've discussed in class before, right? It's harder to deprotonate something that's already inherently negatively charged. So that's an important idea to keep in mind, right? What other factors do we have in play? Right? We've already talked about the fact that carboxylic acids are resonance stabilized and therefore they're inherently more acidic than something like an alcohol. Why is our first pKa lower than what we would expect for a carboxylic acid? That neighboring carboxylic acid withdraws electrons inductively. That's a phenomenon we've seen in several chapters, right? Inductive electron withdrawal makes us have a lower pKa. We are more acidic. Okay? But with that second one, as I was alluding to before, electrostatic repulsion brings our second pKa higher than we would anticipate for that lone carboxylic acid with nothing else going on. Okay? These dicarboxylic acids are also prone to dehydration reactions under the right conditions. And if you have a dicarboxylic acid and you heat it, you can form what's known as a cyclic anhydride in these situations. So for dicarboxylic acids, know you can make these cyclic anhydrides and also know the difference in the pKa values and why. Okay. What else is going on in this chapter? How do I make a carboxylic acid more useful to me? Because carboxylic acids are commonly available right off the shelf to use in synthesis, and they're also common in our bodies. But yet, if you go back and look at the reactivities at the beginning of the chapter, right, acyl chlorides are the most reactive carboxylic acid derivative. Okay. So what do I do to improve my reactivity? Okay. I can activate a carboxylic acid and turn it into that more reactive acyl chloride in the lab by heating it with thionyl chloride or phosphorus trichloride. And those should look familiar. We used those back in chapter 10 to activate alcohols. And here, they're working by converting our leaving group in the tetrahedral intermediate to something better, right? Giving us a better leaving group overall. So you want to know these two reactions to convert carboxylic acids, here they're shown as carboxylates, to acyl chlorides. So how do we do that, right? We've converted to a better leaving group here. So then when I'm exposed to the chloride ion in solution and it attacks my carbonyl to form the tetrahedral intermediate, right? Now I have a better leaving group over here. Right? Better leaving group produces at the end of the day my acyl chloride with SO2 and Cl- as byproducts. Right? Then once we've made the acyl chloride, we're in business. That's our most reactive carboxylic acid derivative. So I can turn that into anything else. Right? I can turn it into an anhydride. I can turn it into an ester. I can turn it into an amide. I wouldn't bother converting it to a carboxylic acid because that's what I started with. You can also activate a carboxylic acid by turning it into an acid anhydride. Okay, reacting with P2O5, this is a less common reaction than the reaction with thionyl chloride or phosphorus trichloride, but it is a valid synthetic route to convert to an acid anhydride, which is more reactive than the carboxylic acid to begin with. Activating carboxylic acids is also something that's common in our bodies. I mentioned that those are pretty bioavailable. So now we're going to look into the world of biochemistry and how cells activate carboxylic acids, keeping in mind that biochem, right, is that interface between biology and our bodies and organic chemistry. Here we're thinking about biosynthesis, which is a synthesis of a compound by a living thing, right? Our bodies are making something. Right? And if we're doing that in the human body, we have to use some pretty different methods than what we would use in the lab, right? In the lab, we can control our solvent. In our bodies, we're typically going to be working with an aqueous environment. So we can't have acyl chlorides or acid anhydrides in your body because then those would immediately hydrolyze to carboxylic acid. So here, right, what we'll see on the next couple slides is using ATP, right, adenosine triphosphate, to convert carboxylic acids into acyl phosphates or acyl adenolates, which have better leaving groups, right? That's what these are showing right here, right? A carboxylic acid derivative with a better leaving group. Then, once we have a better leaving group, right, we've changed our reactivity. And to do that, right, it's just a simple SN2 reaction. We introduced that back in chapter 9. Okay? That gives us, right, an acyl phosphate over here, an acyl adenolate, similar reaction, okay, just done in different enzymes. Right? Then when we have a better leaving group, we've activated a carboxylic acid. Now it's prone to more reactivity, right? More routes in the body. These have to be done by enzymes, right? Because that carboxylate ion, right? We wouldn't have a carboxylic acid in our body, right? Physiological pH about 7.4, right? So that's above the pH of your carboxylic acid. So it's going to be deprotonated. You're going to have a carboxylate anion, negatively charged. ATP, also negatively charged. So if I were to look at those in a synthetic procedure, right, thinking about things in the lab, two things that are both negatively charged, they're not going to interact with one another at all, right? I wouldn't think that those would traditionally react. But when we're inside the active site of an enzyme, like we are right here, right, throw the lab rules out the window. This active site of the enzyme eliminates those like charges and makes it possible to bring those two negatively charged species together. The active site also excludes water, right? Make sure you've got a dry, if we're to shortcut that word there, make sure we have a dry site so we don't have to worry about hydrolysis. So that's just a brief step into the world of biochem, see how chapter 15 relates to the human body. I wouldn't worry explicitly about any of that information with ATP being tested. Right? Know the info on the dicarboxylic acids from the beginning of the video. And note, I am skipping the end of the chapter discussion on sulfur and thioesters, etc. So that'll conclude this video. Keep in mind on Blackboard, you do have the review slides for chapter 15 that are present at the end of the chapter, the sample questions and answers to follow.